Let me start with introducing the people who actually did the work. As you can see, there are a few people from Michigan and also a few people from the other side of the Atlantic. So on the Michigan side, we collaborated with TME and Henry Liu. And then also Professor Dénes Takács was here a few years ago on sabbatical. So we also collaborated a lot on this project at that time. And once he actually went back to Budapest, he included one of his students, Ákos Köpeci. And so the results which I'm presenting today are mostly done by Tian and Ákos, as a matter of fact. So let me start with some motivation. There are many systems now being deployed and tested on our roads, which are trying to get information out of roadside cameras. Okay, these are relatively easy to install. And then now with the new machine learning tools, we should be able to extract, different traffic participants. We can detect them. We can classify what kind of objects we are seeing, and then we can track their motion. Okay, and then typically we got information like, again, type of the road participant, how many are there, their position to some accuracy, and also their speed to some accuracy. Okay? But what we are really restricted in these systems is that we only have a 2D image. We really don't have a three-dimensional information behind. So for example, if you need to really have an accurate position of that vehicle, you really need to know where is that in the 3D space, because that is how far from you. You need to know how it moves in the 3D space. Is it turning? Is it going with a high velocity? And as a matter of fact, we are very much limited if we are seeing these 2D images only. Okay? And these days, there is a big buzzword in AI for this. It's called spatial intelligence. So it's very much popularized by Fei-Fei Li from Stanford. And then they are really saying that in order to somehow, if we want to interact with the 3D world, then we need to get this information from the 3D world and need to interpret it the right way. Okay, so that's kind of what this talk is about. How can we move from these 2D image spaces to the true 3D world? Okay, and in our journey, this started with a very interesting experiment. So luckily at the University of Michigan, we have MCity, which provides us with a fantastic opportunity to do testing. And a few years ago, we were doing a test where we actually were testing conflicts between vehicles. So the way it worked is that, for example, now you can see this view from one of the vehicle's windshield, right? And then other vehicles move around in the intersection. This vehicle is also moving around, and we wanted to time them in a way that they kind of come close, so we can test these safety features and safety algorithms which we are working on. Now, if you ever run an experiment like this, you know that timing is very important, right? So if the vehicles don't start at the same time, then the whole experiment is not worth, because then you're not going to get close to each other at all. And then we actually put a student into this car next to the driver, and the student is supposed to say, when they communicate in the radio and then say, okay, now it's good to go, he's supposed to say go. But this student was a very theoretical-oriented student. He liked to prove theorems, and maybe he was thinking about one of his theorems during the experiment, and he just forgot to say no, right? So what really happened is, we ran the experiment, but this car didn't move at all, right? So first we thought, okay, this is a completely useless experiment. We're going to discard this data. It's not going to be important for us because there was no real conflict happening. The truck is gone. This vehicle didn't move at all. But then we realized we actually found something interesting, because as a matter of fact, this camera, which this vehicle had, it was like a roadside camera, right? At this point, it was on a fixed location. So we were thinking maybe we can use this information to try to extract something from this video, which actually would have been harder if this vehicle is moving, right? Because then every piece is moving here. So what we did was we took this software. It's a freely available software. It's called YOLO. Okay, so it stands for You Only Look Once. Okay, and there's also a famous movie from last year, which is You Only Live Once. Okay, it made a couple of $1 billion in the box office. but this is the first one. Okay, and if you basically take this video and load it into YOLO, then what you're going to see is something like this, right? So it's going to detect the vehicles. It has a good detection mechanism. It basically recognizes if something is running on wheels. And then it's not quite sure it's a bus or a truck in some cases, right? But it does have a good detection, and the bounding box, at least in the image space, is nicely placed, right? But if you really think about, is this something telling me like how far this vehicle is at, what way it's facing, how is it turning or not, then we don't have that information, right? Because in the 2D image space, we don't have that, okay? So then we realize if we want to use this information, especially for automated vehicles, for motion planning, then we need this. We need to know how far is this vehicle and need to somehow extract this information, okay? And there are multiple ways to do it, but we wanted to do it really precisely, okay? So our goal is basically was to, instead of looking at what's on the left, and that's what currently YOLO gives us, it's a bounding box on the vehicle. Now you see, which we call YOLOgraphy, and we'll come soon why we name it this way. You can see a bounding box in the 3D space. I didn't draw the whole box, I just draw it on the ground, right? But I can tell you that's very accurately telling you where is the truck, okay? It tells you in the 3D space where is the vehicle, okay? And then it also tells you its position, its size, its orientation with very high precision, okay? And we also wanted to get the velocity and also the turning rate, or later we call it yaw rate, and with very high precision, okay? So that was our goal, and I'm kind of spoiling a little bit that we were able to do it, okay? And of course, if we are restricted to this 2D image, then we somehow have to figure it out based on the image, and maybe we use much more data from the internet and try to do it. We realized we have a much better way to do it in MCD, okay? Because we could fly, right? So what we did, we actually flew a drone above MCD, just hovering above the intersection. It's about 250 feet we were flying, and it's giving us high quality camera data with 50 frames per second. Okay? And it gives us exactly what we want. It tells us where is the truck, how far it is, and how does it move. Okay? Now, of course, we need to still extract this information somehow, but it looks much easier, right? Because even if I give you this job and say, hey, tell me where the truck is, you could draw a bounding box by hand if you want, right? You would know where is the position, you would know which way it's facing, and so on. If I ask you the same information as a human from the side view image, I'm not sure what accuracy I would get from you, right? If I ask you, like, tell me, what is the truck position, which way it's facing, how fast it's going. But if you look at it from above, that's exactly what we need, right? So we found it to be very promising. And then I'm already showing you some of the trajectory which we were able to get in this case. So we found that this is a very useful data. Now, first, we thought that, what we really want to do is that we always send up a drone for every intersection in the United States of America. And then we are, looking down, we have this fantastic information, and we're always going to send it to the infrastructure, right? And then we talked to a couple of people who said, hey, you guys are out of your mind. This is never going to happen, right? This is extremely expensive, both in terms of money, but also in terms of maintenance. And if you think about how long a drone can fly, it's not going to hover there for 24 hours, not even talking about, wind gust and other issues, right? So we quickly learned that we can do it for a while, and we can get this high-quality information. But at the end of the day, we need to teach that what's on the roadside somehow learns this information, and we only present the side view camera images, and then somehow the side view camera should be able to get this information from the side view after we do the training. Okay, so we are not going to use this information 24/7. We go up, collect information, side view and top view, and then we use it to teach the neural networks which are on the roadside. Okay, so hopefully that kind of makes sense as our goal. Let me go a little technical, okay? So I have two slides where I have formulae. I'm sorry, I'm from the mechanical engineering department, okay? And mechanical engineering is one of the earliest engineering subjects. We very nicely formalized what we have been doing in the last couple of hundred years. So I want to do this because there are some nice information we can read out from these very simple formulae. Okay, so please bear with me. This is going to be slide 1 with some formulae, and there will be a second slide later. Okay, so here's a picture first of the truck. Okay, so actually 2 pictures, right? One is a figure on the top view, and that's on the top. And on the bottom, I'm just showing you how large this truck is. Okay, so this is actually a standard U-Haul truck. It's about 10 meters long. In the United States, actually, you're allowed to drive this truck with a standard driving license. That's not the case in Europe. You would not drive a truck like this with a standard driving license. But here we could do this, and this gives us a lot of great opportunities. Okay? And then on the top, I'm showing you some of the important information which we would like to extract from these images. Okay? So number 1 is the position. We would like to detect the position of the bounding box, in particular the center of the bounding box. So this point C is actually telling us where is the center of the bounding box. Okay. Now, if you want to place an object in a 2D plane, you also need to know this orientation. So that's going to be what we call yaw angle. Okay, and that's the second thing we want to know. And of course, we also want to know how large the bounding box is. Now, if I know the position and I know the yaw angle, I can actually figure out the position of another point, right? Just using geometry. So for example, if I want to know this point R, which is a very special point of a vehicle, it's the center of the rear axle, okay? If I want to know that, then we can actually calculate it with a simple formula, okay? So these are kind of the primary variables which we're going to read out from the images, okay? We also have some derivatives. As a matter of fact, we can get the velocity. So we can take how much between 2 images the vehicle moves. Of course, we measure it in pixels and convert it into meters. So those are going to be those delta XC and delta YC. And we divide it by the sampling time, okay? And the reason I'm showing it so detailed, because you're going to be very careful about it. So typically, if you ask you like how large your sampling time should be, and you would say, well, as little as possible. I want to have these videos with a very, very high rate, right? But watch out for this. Imagine that you have like 10 centimeter inaccuracy in this delta X. Okay, so that's 0.1 meter. And then let's say that you have 100 hertz rate for your information, right? So that's 0.01 second. So actually, if you divide the two with each other, the error of your velocity is going to be 10 meters per second. That's more than 20 miles per hour. That's a large error. Okay, so you really have to be careful how to calculate these. And that's why we often use filters. I will show you the raw data. I will also show you the filter data, okay? And similar thing can happen also with the yaw rate, right? So that's, you check between 2 different frames, what's going to be the orientation difference. And again, you divide it by this delta T, okay? I also want to emphasize that, people in kind of normal day living, use velocity and speed as exchangeable. But in mechanical engineering, no, that's 2 different things. So velocity is a vector. It has a direction, right? Speed only has the magnitude. That's just the magnitude of the velocity, okay? So from the velocity, actually, you can calculate the speed. You can also calculate the direction. So you can actually calculate what we call the heading angle. And you can see that's basically the yaw angle and what we call the body slip angle added together. And that's how we can get out of the data, okay? And this body slip angle is not 0. So the orientation of the vehicle doesn't necessarily tell you, which way the velocity is pointing, okay? There's one special point here, and this is this point R, where the 2 align with each other, okay? And the reason they align, because we imagine that the rear wheels doesn't have too much slip. They don't move to the side, right? Actually, we measured it for a truck like this. When you drive in these urban scenarios, the slip is very, very small, okay? So if you're actually able to track the rear axle center point, that would be the best. But of course, for that, you need to know where is that, right? And when you just look it from above, you will not be able to figure it out, okay? So we typically track the center of the box, okay? But we also track its velocity, and we also track its yaw and yaw rate, okay? So let's see how good the data is, what we can get out of this, okay? So this is one of those runs, which I showed you previously in the video. So I'm showing you the position on the top. So that's the trajectory of the center of the box, okay? And I'm showing you at the bottom the yaw angle, okay? And the accuracy of the position is less than 3 centimeters, okay? Imagine how much you have to pay for an RTK GPS to give you that accuracy, okay? So it's really great accuracy we can get from this position. In this case, we didn't use any machine learning yet, right? We're just using standard classical image techniques, okay? The yaw angle is actually less than 0.1 degree accuracy. By eye, you would not notice that, okay? If you ever try to rotate one of your family pictures, you know, when you kind of take a picture, it's a little bit off, you typically rotate it like, you know, 1 to 3 degrees to make it noticeable. If you rotate it with 0.1 degree, you would not even notice, okay? Interestingly, when you look at the velocity and the yaw rate, they become very scattered. So the raw data is the purple in the background, okay? And as a matter of fact, dot would be very low accuracy, but after the filtering, we can bring the velocity to 0.1 meter per second accuracy, and we can bring the yaw rate to 0.01 radian per second, okay? So this is what we are going to refer as the ground truth, okay? This is what we want to learn from the side view cameras. But in order to learn that, we need to somehow transfer this image from the top view to the ground view, okay? And for that, turns out there is a technique. So this we didn't invent, we just used it, and it's called homography. Okay, so the homography, the idea is that imagine you have a rectangle on the ground, right, which we drew there, and I'm viewing it from 2 different angles. So one is from the top, okay? Of course, if you look at it from the top, a rectangle is a rectangle, right? So that's fine. But if you view it from the side, it just becomes a quadrilateral, okay? And somehow you need to transfer between these 2 images. So if you know the coordinates x and y on one of these images, then you should be able to get the coordinate x prime and y prime in the other one. Okay, and it's given by this matrix with these elements, these h's, which originally you don't know. If you knew that, then you can do this. Okay, so how do we get them? Well, first we collect some static data. Again, this is my second slide with some formulae. Okay, and then basically you just rewrite these equations and say, oh, I have 2 equations and 9 unknowns, and I can solve it. And of course, that you already learned in high school or elementary school, that's not going to work, right? I have 2 little equations. I need at least 9 equations to do this. But it's not a problem because this is understanding that if we have one point on one of these planes, another point on another planes, right? But what if I take, you know, more points in each of these planes? Well, then actually we did that. So this is how it looks. So you can see the top view, and there are those markers which we identified. So luckily, there are some cracks on the road surface in M-City. This came very, very useful for us because we can pinpoint those points to millimeter accuracy, essentially. And we could look at the same points from the roadside view, okay? So this actually gave us more equations, so we could create a big matrix. And if we solve that big matrix, we can get this homography transformation very, very accurately, okay? So that gave us, and the result was quite impressive. So I'm showing you here a video where on the left, you see what we see from the top, and you see what we detect from the top. And on the right, we are simply transferring that image, that quadrilateral now, right, to the right. And the nice thing about it is that that quadrilateral is there even when I don't see the entire truck, right? So as a matter of fact, the corner, the left back corner of the truck is almost invisible for the entire time, right? Even if I ask a human to label this image and say, tell me where is the truck, would be very, very difficult because you don't even see it, right? But the quadrilateral is going to be where it's exactly at, okay? So this meant now we have data. We have very high quality ground truth data. We are ready to do some learning and do some cool AI stuff, okay? So really, this is the first step which we did, which is generated this data, okay? And now you start to understand the graphy part of the YOLOgraphy, right? So this is referring to this homography transformation, okay? Now, we want to do the learning. So now what we want to do is we just look at the images from the side view, and we use this data, which we got from the top, and we want to learn that. So when the camera sees a truck, it's going to tell us, you know, how far it is, what's its speed, how it's moving, okay? And then we put together everything into a loss function, and then we try to use some learning methods to make it simple. As a matter of fact, we didn't change the entire YOLO program. That's a pretty complicated and large software, right? We only played with the top layers of it, right? Because, well, YOLO already knows how to recognize a truck. We didn't want to delete that. We wanted to have something more, okay? So again, the main point is we have an input, and that input is going to be just the picture from the side view, and the output, which the YOLOgraphy is going to tell us, is going to tell us the prediction probability, so how certain it is that it's a truck, okay? It's going to tell us what is the center of the bounding box, so that we will know how far that object is. It will tell us the size of the bounding box, and it will also tell us the yaw angle of the bounding box. Okay, so this is the data what comes out. And of course, as a derivative data, we can also have velocity, speed, heading angle, or body slip angle. So all those things we can actually get from the data by further processing it. Okay, so this sounded quite ambitious. Is it going to work or not? And surprisingly, it worked very well. So if you see the pictures on the left, I'm showing you the yellow rectangle, which is our ground truth. Okay, so this is what we got from this top few images. And then I can also show you the blue rectangle, which is what YOLO learned. Okay, so this is actually training data, and I will come back to that, what happens in testing. And then you can also see this from the bottom left, right? These two objects are put on the top of each other, and then you can see there is a very little difference in the angle, for example. Okay, so they are very close to each other. And then you can also see the picture on the right. So this red cone is kind of showing you what the vehicle, which is the current roadside camera, is looking at. And you can see again that we are very close to what we know as ground truth. Of course, it's going to be less accuracy. We will not going to have the accuracy of sub-degree anymore. It's going to be a few degrees typically. The position is not going to be 3 centimeters, but it's going to be somewhere between 10 and 20 centimeters. So it's still pretty good. And of course, also the derivative quantities are going to have a little less accuracy because of that. Okay, so this is how it looks in an animation, right? So in this case, I just didn't put the picture there, but it's the same intersection, and you can see that we can follow this vehicle pretty well. And then there are two other vehicles we actually recognizing here, two parked cars, right? So those are not moving, so they are less challenging to trace. And sometimes they disappear, right? So why do they disappear there?
The truck is occluding the roadside camera car.
Exactly. So the truck is driving in front of them, right? So it shows us that indeed, even though the system looks great, there will be some limitations here, right? Whenever the camera doesn't see an object, we will not be able to detect it, okay? And of course, this can happen, right? So one of the things we started to think at this point, how do we scale this up? How will we get rid of these occlusions, right? When we have the drone up there, we know everything, but when it comes down, we are relying on the side view cameras, okay? So now if I show you again as comparison in terms of accuracy, you can clearly see there is a degradation of accuracy. For example, if you look at the yaw angle, the orange curve is telling you something which is very, very accurate. But when you compare it to the blue curve, right, the blue is kind of more hairy. So then we will have a decrease in accuracy, okay? So then the last thing remained is that I mentioned you, this is training data. Now, one thing can happen if you ever do machine learning is this, I think we always run into this, at some point you start to overfit the data, right? So you basically got very, very good agreement between the training data, but it turns out if you show another video for this YOLOgraphy, then you would get something probably quite errors, okay? And we needed to make sure that that's not the case here. Well, the issue was that we only had one video, right? So we only had the video when my student didn't say now, okay? And then what do we do? Well, we were thinking, well, we should go back to MCD and to get more data. But then we also got a little more constructive. We said, well, we probably shouldn't just park that car there where it was. First of all, it would be difficult to put it back exactly to the same position. And in order to get the homography information, you actually need that, right? So you need to have the camera at the same position. The second thing is that's not very practical, that you just park the car there because it would block the rest of the traffic, right? So we were thinking, well, let's go back, let's get more data, and let's take advantage of the fact that MCT actually have an infrastructure which is even being built today with the MCT 2.0 project, where we can actually use high quality information from roadside cameras through roadside cameras, okay? So that should allow us to do the last step, which is the testing, right? So here I'm just showing you that that's gonna be giving roadside images to the camera, which the camera have not seen yet, okay? And asking the camera to provide us with this information, okay? So once we went back, then of course, first started to kind of figure out what kind of experiments we should run, okay, how many vehicles we should move around. So here I'm showing you one when we moved 5 vehicles, and we did many of these different configurations, but I'm going to show you only this one today. And you can see that as the vehicles are moving, we can actually track every one of them, okay? So here we decided we're only going to track the moving vehicles, but of course you can always detect the part vehicles as I showed you before, okay? So once you run an experiment like this, the ground truth data looks something like this, okay? So this is going to be what you trace, and these will be the individual vehicles moving on the road surface, okay? So then we also wanted to see, okay, can we get the extracted information from this? So indeed we did. So we get the path information. So on the left, I'm showing you the filtered and the unfiltered data, but they are very, very close to each other. So as a matter of fact, in terms of path, the filtering doesn't help so much. In the middle, I'm showing you the yaw angle, okay? And that's again filtered and unfiltered. This is a little bit less perfect. So this is shown for the red car. It turns out it's actually harder to track cars than trucks, because trucks are really rectangles. Cars are a little bit off in a rectangle, right? And you can see actually there is a swing at some point around 12 seconds when the yaw angle actually changes about 1 or 2 degrees, okay? This happened rarely, but I wanted to show you this, that indeed this is not a perfect system, okay? On the right, you can see the speed, okay, of the center of the box. You can see the row speed would be completely useless, right? So that's the gray figure. But the filtered one is actually showing pretty nicely how the vehicle was driving, okay? Interestingly, this driver was kind of reducing the speed during the turn, and it was not doing kind of a nice smooth movement, okay? So this is what we could get from multiple vehicles, and I have to say, this was a harder task than we thought originally. So we were very confident when we had the truck information that we're going to do all the cars very quickly. Turns out when you start to scale up an algorithm, there's a lot of engineering you kind of have to go through, okay? Now, the other thing we wanted to do, and I mentioned that this was important, is that rather than parking the car there, we started to use MCT's infrastructure, okay? So if you go to this intersection at MCT, so this is the intersection of Main Street and State Street, and I feel it kind of there is a little bit of reference here to the city of Ann Arbor, though in city of Ann Arbor, Main Street and State Street are actually parallel to each other, while in this case they are actually perpendicular, okay? So I'm showing you a grid, you know, from the top. This was actually what the YOLO itself was using to do this learning, and I'm showing you this grid from the 2 different camera views. One is what we call the northeast camera. So this is on the northeast corner of this intersection. Another is the southwest camera, which is indeed at the southwest intersection. Okay, so I'm showing you the same picture actually from these different views. And you can see to make sure that you kind of have a better understanding, I also put a unicycle there. I will mention you at the end, you know, what is that about, okay? But at this point, you can see that rider in 2 different positions, okay? So now we have the infrastructure, we have the methodology, and they were like, okay, now we're ready. We just load the data, just gonna learn everything. And then quickly learn that, wait a minute, everything is not as nice as in the first experiment. If you actually look at what the camera sees, for example, you look at the northeast camera, it doesn't quite see the entire intersection, right? You can see the kind of the sides are chopped off. Some of them actually we had to cut off because of the learning methodology, but even if we leave it there, you would not be able to see the entire intersection, okay? You see a pretty good view of part of it, but some part is missing. The same thing happens from the southwest camera, right? We will not see everything, okay? And this kind of gave us a challenge because, you know, when we look at from the top and we're looking at this image, Now the camera is seeing the red car and the white car, right? So they are kind of marked up with these rectangles, but the truck is just entering, okay? So the truck is only going to be visible in part of this journey, right? In the previous example I was showing, we could kind of see the truck in the entire journey, okay? So as a matter of fact, not all the data we collected is going to be useful for the learning. We learn that quickly, right? So if I kind of plot you the ground truth data and I show you this cone, only the yellow part is useful for learning, and the gray part we just have to discard. That's not going to be useful, okay? Luckily, we have another camera, so kind of that helps us out a little bit. So if I'm looking at from the perspective of the southwest camera in this case, right, you can see the same example. Again, once the vehicles move into the cone, then suddenly they become useful for us, right? And now you will see the red vehicle moving in and the white vehicle moving in. So again, part of this data is useful, but part of the data, which is when they are outside, that's not going to be used, okay? So we have to discard. And that's why I mentioned that once you start to scale up, there's a lot of engineering problems which are coming up, and you need to overcome those. Okay, so in this case, that's going to be the data which is useful for us, and this is what we're going to use for learning. Okay, and just to show you everything together, so here I'm showing you the top view, right? So vehicle starts to move soon, and these camera pictures are coming up at the point when one of the vehicles enter their viewpoints, right? So now you can see how they are moving around, and now they are synchronized. So at this point, indeed, we had to learn a new homography transformation for every camera, right? Because they are looking at that intersection from different angle of view. But we did that, so we're using one homography on the bottom left and one homography on the bottom right. Okay, so this allowed us to basically process the data, and at that point, we said, okay, this is our ground truth. We are really ready for learning, okay? And I showed you previously some testing data, and they were really, really great. Now, training data, excuse me. They were really, really great. I want to show you some testing data. So the video I'm going to show you, YOLO have never seen, okay? It have seen similar things, right? And let's see what it can do with it, okay? So in this case, we start. At the beginning, we are not detecting the cars because they're a little far. But now they're coming in. You can see there are some ghosts popping up here and there. But in general, we're doing pretty good, right? So indeed, in this case, our accuracy goes down, right? So you can see the boxes are shaking more, maybe a few degrees. But in order to get this information, if we can filter it a little more, we can still get it very useful for other traffic participants, okay? So if I show you how does it look like when I just look from the top, I mean, this is the cone where we can do anything. This is where we can do the detection. And you can clearly see that the detection got a little worse, right? So there are some missing points when we are not able to track the objects, okay? But it's in particular the part which is in the kind of center view of the camera, we're doing pretty well, right? So that's why the vehicles which taking the left turn, so they're coming from the west and taking the left turn, they are very nicely detected, okay? So if you compare it in terms of like the process data, then this is roughly what you get. So you can see the path on the left. Well, even by naked eye, you can see a little bit we are off the ground truth, right? So now our accuracy is not a few centimeters, but maybe 10 to 20 centimeters, okay? In terms of the yaw angle, we're doing pretty good, but there are some parts when, we are a couple of degrees off, okay? Sometimes I think the biggest we've seen was maybe 10 degrees, which is still pretty good in terms of detection. So we are still capturing what is happening. Of course, we are only capturing part of that motion, right? Because that's what the camera sees. Now, when we're looking at the speed, okay, the speed is about, I would guess, 1 meter per second accuracy. That's actually pretty good. And that's about 2 miles per hour. A few years ago, we did a highway test with 2 vehicles of a company, which I'm not going to name. And we learned that about 1 mile per hour is the accuracy of the cruise control. And the way we learned it is because we had to set one of the cruise control exactly 59 miles per hour and the other cruise control exactly 60 miles per hour to make the 2 vehicles and not have the distance changing, okay? So you quickly learn that that's roughly the accuracy which the industry is producing. So if we have a 2 miles per hour prediction accuracy of other vehicles around us, that's actually pretty good. Okay, so that would be nice. And of course, again, we only see it in part of the case, and the error may be larger at the edges, and that comes from the fact that we are running a filter and there is no more data there, right? So that's why typically you get larger inaccuracy at the edges than you got in the middle. Okay, so hopefully this convinces you that indeed this is a viable technology. And then just to kind of, as a reference, I also show you this from the southwest camera. Okay, and then you can see, now we can see the truck more. Okay, so it's turning nicely. Again, when a truck is very close to us, then we are not very good on getting the angles. And then you can see the other vehicles are also sometimes a little rattling. And as you can see, YOLO sometimes put their ghosts, right? So this data is not really post-processed. I really wanted to show you like how the kind of raw learning data is looking, right? So for example, suddenly it put there a vehicle, this something has to be filtered out. Okay, so if you look at, for example, in terms of the top view, you see some of those dots kind of put in the middle of nowhere. Indeed, these are ghost vehicles. But that's why, you know, we have multiple cameras, right? So in this case, this is just what one of the cameras sees. And then we also have a number of the detection accuracy, right? So that point may be detected with, 50% accuracy. You might discard it immediately, right? And again, if you look at in terms of the accuracy is similar in terms of the yaw angle and the speed. And now you can see the effect I mentioned, that the end, actually, there is a little bit of, there is larger inaccuracy, and the speed actually is pretty large. And that's again because basically the filtering window is of certain size, okay? Having said that, still we are pretty happy with this. And luckily we have two cameras, so we can put it on the top of each other. So now you can see that, for example, one of the cameras completely missed the truck coming from the east, right? So the dark blue curves, they are not showing at all because it's just not on the picture, right? But the other camera detected it perfectly well and with very, very high accuracy, right? Similarly, there are other sections where, the other camera is doing a good detection, and then we can actually put it together. So indeed, lesson learned. If you want to do a real implementation, put on at least 4 cameras, right? So for an intersection, that makes sense. Get those angles right, and there is a lot of kind of engineering going there. But if you do so, then you can basically capture anything moving in that intersection. Okay, so that's a really nice feature. And indeed, that information becomes very useful for many traffic participants, right? So if you have an automated vehicle, this information can be sent to the automated vehicle using the roadside units, right? So because this information indeed will be processed on the edge, right? You don't have to bring it into a traffic center. You can just process it there because your camera is already trained and everything is working fine. You may have to retrain it, right? Seasonal changes happening. 3 days ago in Michigan, winter arrived, and the next 5 months, I'm just telling everyone, there's going to be winter here. That's for sure. Okay, so you may want to retrain this, but flying 4 times a year the drone is very different from flying 24/7. That's not going to happen. But if you fly in the 4 different seasons, that should be fine. And then this is allowing you this as information. If you want to bring it into a transportation center, right? It's like, for example, M-City has this fantastic facility that we can get any data collected on the track and bring it into a common center, then you can also do that. And you can use it for detecting many different things. You can think about safety, how vehicles are getting close to each other. You can thinking about traffic throughput. You can thinking about how the vehicles are moving. So this is going to be a very, very valuable thing. And indeed, at the city of Ann Arbor, my colleague Henry Lee has a very nice installation down in the south of Ann Arbor where they put up 4 cameras and they are trying to and they got the data 24/7. So that's real traffic data with a real installation. Okay, so this is clearly something which is possible, and using these learning techniques is supporting this kind of research. Okay. So I have 2 more slides, okay, to make sure that I finish in time. So one is, I just wanted to show you that if you're interested in reading more about this, there is a journal paper which we already published, and there's also a conference paper we already published. And that was actually presented to vehicle engineers because we're really interested in, what is their view of using these new kind of image-based technologies. And I think in general, we got a lot of good feedback. And then we also have 2 US patents. So thinking about commercialization, then we're also kind of on track with that. Okay. My last slide is a little bit of a curiosity. Okay. So I mentioned you there was this unicycle hovering around, and you have seen it on many of different videos. Okay. So we were really interested in, like, can YOLO do something with this? Okay. Not talking about a YOLOgraphy yet, just a YOLO. So we just loaded this video and tell YOLO, can you please track this device and tell us what it is and what is it doing, right? In this case, of course, we only have the side view in this case, right? And you can see from the initial image that YOLO is not quite sure. Is it a person? Is it a bicycle, right? It's kind of debating it, right? Now we are kind of running into this problem just a few days ago in the news, something is a human or a humanoid, right? If you read the news, what I'm talking about, right? So here you're not quite sure, is it a person or a bicycle? But then we run it for you because you will see that it's still debating itself quite a bit, okay? And at the end, it concludes that it's a snowboard, okay? As a matter of fact, it went through a couple of more arguments. It was difficult to see, but I kind of come back to you here. So it's still a person. If I go a little bit more, at some point it believes it's a frisbee. Okay. Actually, at the end, it started to conclude that it is a skateboard, right? But then it realized that finally it's winter in Michigan, so it must be a snowboard. Okay. So solving this problem, we haven't. But I really appreciate you coming and listening to me today, and I'm very happy to answer any questions.
There's grid smart cameras, fisheye cameras at that intersection as well, which is also what the project you mentioned that Henry's running uses. Did you look at any of the fisheye data in this work?
Yeah, so I have a confession. This whole idea, and this was a project I think they both worked on a few years ago. This is where it actually came from. So we're talking with Henry about this, and then one of the questions was that what is the ground truth data they are using for the fisheye, right? Because that also has to be trained. And it turned out that, at least at that time, this was all human labeled. So basically, someone was looking at that fisheye image and clicking, these are the corners of the vehicle. And they realized that this is extremely labor intensive. At that time, the fisheye cameras was giving us data about, I think, 0.4 hertz. So in every 2.5 images per second. Here we have 60 frames per second. Hand labeling, this is out of question. So actually, that was the main motivation, that even in that case, we needed some kind of ground truth information. And then, of course, we also wanted to kind of use it for learning, and that's why we use the MCT cameras. We haven't gone back to the fisheye camera. So at this point, we kind of still using the MCT data set. But indeed, that helps a lot because you have a much better angle view. But some of these techniques are still very useful for that as well.
Yeah, I guess I was wondering, has anybody flown a drone? Oh, you mentioned State and Ellsworth, right? Where the four corners have fisheye cameras. But that's not, I think, LiDARs as well. So we would know some ground truth from that. But wonder, it'd be interesting. Have you ever taken drone data at any of the smart intersections in Ann Arbor?
So I haven't. As far as I know, that was not yet done. Flying drones, for us, it's a little difficult at the university. We need a different authorization. MCT is much easier to do. But certainly, if this project continues in one way or the other, this would be the next step to kind of go out to the real intersection, right? Here we were kind of mimicking traffic for our own benefit, but indeed, that's the real test. So sending up a drone at State and elsewhere would be something very interesting, and then we can kind of compare the fisheye images and do the same thing. So compare the ground truth with the roadside fisheye cameras.
Topic or question. YOLO is nice because it's deployable at the edge, but there's some really great foundation models coming out, open weight, like Qwen 3 vision language model. Have you thought about looking at any of those? They would be more sort of like, they'd have to run on the data center. They wouldn't run on the edge, but they could also be potentially useful for annotation.
Yes, so we have two answers to that. So indeed, when we started to do this, then kind of YOLO was the state of the art. We are actually not kind of fixated on YOLO. So basically, any image processing technique we could use for training. We just happened to choose it at that time because it was good. Definitely thinking about, new models, new foundation models to do it. Interestingly, you mentioned that currently they are running on data centers, but with the distillation of these models, it's actually not unimaginable that in a few years they will actually be able to operate it on edges as well. I already know that, for example, the GTPs, which are for languages, there are versions you can actually install in your computer, and of course that model is not retrained, right? So it's kind of a frozen model. But if that's what you want, then it's possible to run it on a standard computer. So I think there is a lot of potential here, and then I think our technique is agnostic to what is actually the neural network or the image processing in general using, and in any of them can utilize this high precision information, as a matter of fact.
Thank you very much. Really nice presentations. I actually have two ideas. First one is in your example slide, you use two different cameras for two different training. Were you thinking about combining those, like kind of using together?
Yes, absolutely. So clearly that's our next step, and because at this point we were doing it separately, we wanted to see what we can do. As a matter of fact, it's kind of really makes sense to put these together, right? And then you can do it in a parallel fashion or an integrated fashion. Probably that's a better way to say. So yeah, absolutely.
Yeah, interesting. Second one related. I know a lot of like intersection here in Ann Arbor. They also have radar installed and radar installed. Do you consider multimodal sensing using?
Yes, so that's a very good question in two ways. As a matter of fact, I didn't talk too much about it in this presentation, but in some of the when the truck was running, the truck actually also had RTK GPS on the top of it. So we actually also knew when the truck was high accuracy from GPS, right? Because we wanted to kind of cross-check it. And in our first paper, actually, we argued against that. We were saying like, well, it's only possible with a few vehicles, right? So you won't be able to do this ground truth data from RTK GPSs because that's typically not installed. But you mentioned LiDAR. So LiDAR actually is indeed a viable alternative. As a matter of fact, there is a highway intersection close to Budapest in Hungary. It's about 800 meters long. And that's what exactly they did. So they had cameras and they also had LiDARs, right? So their ground truth data is kind of coming more from LiDAR rather than, for example, flying drones. After all, it's a highway, right? So that's a much harder thing than an intersection, right? In an intersection, it's easy to hover a drone around. In a highway, like you would only see a certain section. So yeah, certainly that's possible. It's very non-trivial how to do the data fusion for LiDAR and camera, in the sense that probably there are many solutions for that. I know that the team in Budapest came up with one viable one, but this is a kind of an additional thing you need to do if you want to do that, right? Because then you have to kind of fuse somehow these two data. So we're not saying our solution is good for all the scenarios, but for many scenarios we found it kind of cheap and easily deployable. After all, flying a drone, it still sounds easier and more flexible than installing a LiDAR sensor, which, by the way, you also have to validate. So if one of the challenge in this installation I mentioned on the highway was that they had to validate the LiDAR data, and they indeed did it with super high precision GPS, right? And that's, again, something which is not easy to do for all deployment, that you instrument a car with a 200K GPS and keep running, right? So I think that's it's a viable solution, but may work for some scenarios. This may work for others better. Again, we kind of promoting the lightweightness of this installation. So with very little added infrastructure, we can provide high quality data for the cameras.
Okay, we have one online. Picking that up. What about using this technique in poor weather? Can you use infrared cameras?
That's a very good question. And the general answer is yes. As a matter of fact, if you looked at some of the videos, the vehicles had some big patches of orange rectangles stuck on them. And that was because we were actually thinking about doing different camera processing at that time. This was just normal camera, not infrared. But we were thinking, oh, as a matter of fact, if you do have a marker, right, which you can trace, then even in bad weather conditions, you can do it, right? So certainly that's an option. We haven't done it, but if you want to do, you know, night training and so on, that's probably something where you kind of want to rely on those different camera modalities.